Alright, we're going to wrap up chapter 2 pretty quickly, and then we're going to start chapter 3. Okay? Resonance. That's the piece we have to cover before it's done. What is resonance? I know you went through this in Gen Chem 2. Right? And also Gen Chem 1 actually. Do you remember? Ozone, for example, right? That's the example you have. O3. And then you have something like this structure. Right? And then probably you did like this. And then you have the double bond on the other side. There, or something like that. That's the example you saw in Gen Chem. So can you define based on that structure? What is resonance? So if you compare these two, what are the things that is not changed there? So that's the sigma bond, right? This is sigma, sigma, and then 1 out of 2 is going to be sigma bond, right? We saw that in sp, sp2, sp3 hybridization with the carbon before. Same thing, right? So sigma bonds are not changed. You have the same number of atoms there. There is no change on that. So what is changed? Pi bond, right? So if I do with a different color, so the change you have is this pi bond over here, and then this over here. Right? So the first of the double bond will be sigma, remaining going to be pi, right? So you know how pi bonds are formed. Overlap between the pure p orbital, right? That's how it is formed. So if I draw the orbital here, this is pure p, let me write pg, right? And then you have same thing pg over here for the other oxygen, right? Now if you see on the other side, you have the same thing. This is pg, this is pg, right? You also have orbital on oxygen over here. So these are also pg, 2 pg you can write that, right? So pg, right? So if you count the p orbitals, you have same, there is no change on that. Right? Of course, for sp2 hybridization, you have 3 sp2 hybridized orbitals. We have not shown that. That's for sigma bond. Right? So now, what is the difference then? Now you can answer based on the picture drawn over here. The difference is the overlap of p orbitals. Okay? In the first structure, you have the overlap over here on the left side. So you have here overlap, so you have the pi bond from there. Okay? You don't have any overlap on the right side of the left structure there. Right? But what about the right side? You have overlap over here. So you have the double bond on the right side, right? So this is also overlap. That's the only difference. So based on that, you're going to have structure with the double bond in different locations. That's the resonance, right? So the cause for the resonance structure is the overlap of pure p orbitals in different parts of the molecule. So now you're going to apply the same concept over here. NO3 minus, right? You apply the same Gen Chem concept over here. It's not different, exactly same thing. So you have NO3 minus. Right? This is an ion. Okay? So if you draw that, you can draw the same thing like this. Right? So this is NO3 minus. Showing all the atoms there. Right? Now the question is, how many valence electrons you have there? So for the oxygen, how many? Oxygen you're going to have 6, right? Total 8. You're going to have 2 electrons on one s orbital, and then remaining going to be valence, right? What about the nitrogen then? You have 3 of oxygen, right? You have 3 times that. So you're going to have 6 times 3, 18 total valence electrons, right? What about the nitrogen? 1 less than oxygen, right? So you're going to have 5, right? 5. Do you have any more electron than these? You have here, right? And that. So you're going to add plus for that, plus 1 for that. Now what is the total? 18 plus 5, 23, plus 1, 24. So you're going to have total 24 valence electrons for that ion. So now you can use these electrons to make the bond around the atom, so that all atoms in the molecule, in the ion, going to have octet. Okay? So what are the possibilities? So this is one. So one possibility is this, right? You have this one. So you have the double bond. So let me write 1, 2, 3 labeling for oxygen, okay? To make it easier. So you have the oxygen 1. This is just a label, right? This is oxygen 2. And then this is oxygen 3. I'm going to do the same labeling for other structures. So I'm going to do 1 over here, 2 over here, 3 over here, right? 1 over here, 2, 3. So now if you compare 1, 2, and 3, what do you see? You have octet in all these 3 different types of arrangements, right? You have the same number of atoms there. You have the same number of valence electrons there if you count, right? You have the same number of sigma bonds there. All atoms are sp2 hybridized. How do you know? You have the double bond there, right? So now, what is the difference then? The difference is this. So for the first one, you have the double bond with oxygen 1. In the second one, you have the double bond with oxygen 2. Third one, you have the double bond with oxygen 3. There's the difference. So the overlap between the p orbitals, that's the difference. Right? So now, these are also resonance. Okay? So sometimes you're going to write the resonance hybrid structure. So the mixing of all 3. Right? So how do you write that? So you're going to write O, N, O, O. So these are sigma. This is fixed, right? So you don't touch that. So now for the pi bond, what do? You're going to put on all of them. So you're going to put dotted line for that. So you're going to have this. You're going to have this one. This one. So this is the resonance hybrid. So resonance hybrid. That's how we're going to write. So in organic chemistry, this class and OChem 2, you're going to see the resonance structure all the time. When you write the mechanism in particular, we're going to use the concept. Right? So now it is clear for the resonance. So the cause of resonance is the overlap of pure p orbitals in different parts of the molecule or ion, whatever you have. Right? So that's how we're going to do. Okay? So now, sometimes it is a little bit tricky. If you have the resonance form, then how to know which type of structure is going to be more probable, which is going to be a little bit less probable, like that, right? So we have some rules for that. Okay? There are 4 rules. We're going to follow that whenever you come to compare the different type of resonance structure. Right? So number 1 is you're going to choose one particular type of structure more probable if you have more number of bonds, in particular the covalent bond. For hydrocarbon, you can have covalent, right? So you're going to count that. So let's say these two. So you have carbonyl functional group there, CO, right? And then you're going to have CO, but you don't have double bond over here. You have the charge, right? So in these two, which is going to be more probable? So you're going to count the number of bonds. So for the left one, you're going to have 2 bonds for CO, right? And then 1 bond for CH, other for CH. So 1, 2, 3, 4, right? You have 1, 2, 3, 4. You have 4 total bonds there. Okay? What about on the right side? How many? You can count them 3, right? You have 1, 2, 3. So 4 is greater than 3. So the one with the 4 bonds is going to be more probable. Okay? That means most of the time you're going to do the reaction. So the 4 one on the left one, that's the one you're going to take for the reaction compared to the other one. Right? That is more probable. Okay? So now, second rule, going to say that if you have more atoms as octet electronic state, that's going to be more probable. Or the same thing, if you're going to say the other way, the molecule or ion with the least number of incomplete octets, that's the one going to be more probable. Okay? Let's see over here. This one, the first one, and the second one. So which is going to be more probable or more contributing? So you're going to see the octet state. So for the oxygen, in both cases you have octet, right? If you count all the electrons there, all oxide atoms have octet, right? What about the nitrogen? On the first one, how many electrons the nitrogen has over there? 1, 2, 3, 4, 5, 6. Right? You have 6. So it does not have the octet. It is incomplete. If you have 8, it's going to be complete. Right? But on the right side, how many? You have 2, 4, 6, 8. You have the total 8 electrons for the nitrogen. Right? So that is complete or filled. So you have complete octet there. That's why it is more probable than the other one. You can have more than one atom in the molecule or ion. So the more atom you have complete octet, that's going to be the more probable one. Right? You're going to take that when you do the reaction or mechanism. That's number 2. Okay? Number 3, So these two are a little bit less important than the first two, but still, if you have a draw on number 1 and 2, you're going to break the tie from here, 3 and 4. Okay? So for this, it has a less separation of the unlike charges, plus and minus, right? So you have less separation of that. So for the first one, you don't have any charge on the atoms there, right? But for the second one, you have the plus, minus. That's the separation of charge, right? So both electrons for the double bond go in one side, of course, to the more electronegative atom, right? So you have the minus of the oxygen, so that's not more probable, right? So the first one is more probable because it doesn't have any separation of charge. If you have charge separation on both, you're going to see the less charge separation state, right? And the number 4th one, it has negative charges on the more electronegative atom. That's the obvious one, right? So electronegative atom going to have more tendency to draw the electrons or the bonding electrons. They're going to break it, right? So if you see over here, the first and second one, this one, this one. So what's going to be the more contributing one? So if you see the charge, you have minus charge over here, but the oxygen does not have minus charge. Do you think carbon is more electronegative than oxygen? No, right? So the oxygen is supposed to have it because oxygen is more electronegative, right? That's the reason why you have this one in which the oxygen has a negative but not the carbon. So this is more probable. So the more electronegative atom should have more negative or negative charge compared to less electronegative. So these are the rules. Whenever you wanna choose like which is the more probable resonance structure, you're gonna take account into 4 rules. Okay? So that's all about resonance. Alright? Good? Any question on that? Alright. If you don't have any, then we're going to go to chapter 3. So, now you're going to learn a little bit new. So for chapter 4, again we're going to review some of the Zen chemistry stuffs. So this is I'll say new compared to 2nd and 3rd chapter. That's the 4th chapter, right? So this is alkane and cycloalkane. So we're going to see the properties of these, in particular the conformations. So if you change the position of atoms in the molecule, what's going to be the structure of that? That's what we're going to see. Okay? So now the point is, what is alkane? So we're going to define from there. Right? So you touched a little bit on Zen Chem 1, like some functional groups and alkane, brands, different types of alkane, right? So we're going to go from the beginning. So alkane is hydrocarbon. That means you're going to have the carbon, you're going to have the hydrogen, right? So you're going to have the modified form of that. If you have any functional group, that's fine. But essentially the alkane is going to be the hydrocarbon in which carbon going to have only single bonds. Not double, not triple, right? So if I write carbon, it's going to have all all single bond, and then you're going to put the hydrogen to satisfy the bonding there. This is the simplest form of alkane. You have the carbon there, hydrogen there, this is hydrocarbon, right? So carbon have all single bonds there. That's the hydrocarbon, right? So how to name that? We're gonna go through the nomenclature process in detail, how we're gonna name these compounds. But at the beginning, we're gonna see how many carbon gonna be there, how many hydrogen gonna be there. That's the formula, right? So in any hydrocarbon, the number of carbon and hydrogen is based on this formula. You're gonna have Cn, n gonna be any number, 1, 2, 3, 4, 5, 6, 7, whatever number you have, right? And then the hydrogen gonna be 2 times that n plus 2, right? So that's how many hydrogens gonna be there. So for example, for the simple molecule, for this simplest hydrocarbon, how many, or what is the value of n there? 1, right? So you have C1, only one carbon. So if you have C1, then how many going to be the hydrogen? So hydrogen, you're going to use that. So 2 times n is 1, right? Plus 2. So what's going to be the number? 4, right? That's why we write that. C4. Suppose you have 2 carbon atoms there, right? So I'm going to write C2, or I'm going to draw like that. I have 2 carbons there, okay? So now, I don't have any option for the multiple bonds for the carbon. All should be single bond, right? I'm going to write 1 over here, 1 over there, 1 over here. So carbon cannot have more than 4. 4 is the optimal bond you're going to have. So I can write that. Okay? So now how many hydrogens there? The same formula. So I'm going to do 2 times n. What is n? 2, right? Plus 2. So 4 plus 2, 6. So I must have 6 hydrogens there. So I'm going to write 1, 2, 3, 4, 5, 6, like that. So you're going to go all the way to whatever number of carbons you're going to have there. Right? So let's say gasoline or fuel, right? So octane, this is the name of that. We're going to go to the nomenclature. So you have the C8 for gasoline. So how many hydrogens going to be there? Same formula, right? So you're going to have 2 times 8 plus 2, 16 plus 2, 18. So you're going to have S18. That's the octane, right? So that way you're going to have any number of carbon there. So the hydrogen is going to be based on the number of carbon you have there in such a way that carbon is going to have only single bonds. No double, no triple. So this is for a different chapter. We're going to have alkene, alkyne, we have different chapter for that. But this chapter is going to be only single bond. Okay? So now, you know the structure of the molecule, right? So you know number of carbons you have. Alright, so now, the next thing going to be orbital. So now this is not new, so you know that, right? How many types of molecular orbitals you're going to have? Let's say the simplest one, 2 carbon, right? Or you can take 1 carbon, doesn't matter. If you have 1 carbon, so what's going to be the orbital? I mean the hybridization. sp, sp2, sp3, what's going to be the hybridization on the carbon atom of this molecule, methane? What do you think? CS4.
SP.
sp? Okay. sp. Do you all agree with that?
No.
If you all agree, then it's going to be a red flag. What do you think?
It's SP3.
sp3, not sp, right? So in which condition you're going to choose sp? When you have the triple bond with the carbon. Remember that?
Yeah.
And then for sp2, when you have the double bond on the carbon, right?
Yeah.
You're going to choose sp3 when you have only single bond on the carbon. So you have all single bond over here, right? So you're going to choose sp3, not sp, not sp2. Okay? So now for that, that's the reason why if I choose carbon over here, I'm going to have that one sp3, I'm going to have another sp3, I'm going to have the third sp3, and then I'm going to have the fourth sp3. So all are sp3 hybridized orbitals, right? So now you're going to put the hydrogen, 4 hydrogen, you're going to have 1 there, 1 there, 1 there, 1 there, right? So all are hydrogen. So that's how the bond is formed. So now my question is, what is the name for that bond between the carbon and the hydrogen? Sigma, right? So why sigma? It is made from the head-on overlap of sp3 hybrid orbitals. So you can have the pi bond only if you have the bond formed by the pure p orbital. There is no pure p. They are all hybrid orbitals, not pure, right? So now the same thing over here. So you're going to have 2 carbon there, and you have 3 hydrogens there, right? For example, shown over here. So you have all sigma bond with the hydrogen as well as between the carbon. Because this is also sp3, this is also sp3, you have the sp3, head-on overlap, and that's going to be the sigma bond. Always. Okay? So that's the sigma bond. Very stable. Stronger than the pi bond. Because you have the head-on overlap, or you can say the maximum overlap between the orbitals. Okay? So now, remember it is sp3 hybridized. Okay? Always. If you have alkane, always going to be sp3. There is no exception at all. Right? So this is always for alkane. Doesn't matter what alkane you have. Doesn't matter how many carbons you have there. All carbon going to have this single bond with them. That is going to be sp3. Always. Okay? So now, the next thing going to be, what is N? So this is for normal. So N is for normal. Okay? So you can write like N-butane, for example. You can write N-propane, pentane, right? So all are alkane. So in general, you can write N-alkane. Okay? N-alkane. So N is normal when you have all the carbon atoms in a chain. They're going to make the straight chain without any branch. Okay? So, for example, if you have 4 carbon atoms, I'm going to write each carbon in the linear chain. Okay, 4, 5, 6, whatever number of carbon you have. If I write all in the linear chain fashion, that is called N-alkane. Okay? For the same 5 carbon, for example, I could write this way too. So 3 carbon there, and then 1 carbon over here, right? Something like this one. 1, 2, 3, 4, 5. I have the same number of carbon, but it is not linear. I have the branch connected on some of the carbon in a chain, right? So this is not N. So this is not N-alkane. So we're going to see the examples later. Depending on the number of carbons, you're going to have different name on that. These are branched alkane, right? But as long as you have the all carbon atoms in the linear chain without any branch in it, this is called N-alkane, or the normal alkane. Okay? So, now we're going to see what kind of interactions are going to be between the alkane molecules in the sample. If you have, say, 1 liter of gasoline, how many molecules of alkane are going to be there? Billions or billion molecules, right? So what is going to be the interaction between the molecules in the sample? So for that, we're going to review quickly on the GenChem 2. You went through the intermolecular forces in a sample, right? So this is the summary of that. What are the ionic interactions? If you have any compounds, right? So if you have the minus charge, if you have the plus charge between the molecules, then you're going to have the ionic interactions. These are when you have ions in the sample. Okay? Second going to be the hydrogen bonding. So hydrogen bonding and the dipole both are on the same class. Actually, you can put together, right? So what is that? If you have the polar bond, let's say CH3Cl as an example. So you have the CCl bond and you have 3 hydrogens on the other side, right? Now, if you see the electronegativity difference between carbon and chlorine for the CCl bond, of course, it's going to be more than 0.4, right? Remember we calculated before, right? So that means it's going to be polar. So it is covalent, they shared electrons together, but the bond is polar. That's the reason why you're going to have minus, slightly minus there, slightly plus on the carbon, so the bond is polar. If you have any that condition, the polar covalent bond, you're going to have the dipole interactions, right? So 2 poles, you can write this way. So this molecule, minus on one side, plus on the other side, so you have the polarity, right? So the minus side of one molecule going to interact with the plus side of the other molecule. You have billions of molecules there, not only single molecule, right? So that interaction is called dipole interaction, right? Can be any molecule, HCl for example, right? So carbon, nitrogen, for example, alcohol, right? So you have the same polarity there. So if I write methanol, for example, COH, and then you have the hydrogen there. So same thing. You have the minus over here, and then you can have the plus over here like before, right? So you have the dipole interaction there. Now, when you have the hydrogen attached to oxygen, nitrogen, halogen, for example, right? Then what are you going to have? Hydrogen bonding. So you have the same thing, plus going to be over here. So oxygen is more electronegative. If you have the hydrogen, that's the special class of dipole. So we're going to call that hydrogen bonding. Okay? So you have the hydrogen interacting with the oxygen to the other one. Like I can write this way, right? So carbon. So now you have this interaction too. So this is called the hydrogen bonding. Right? It's still dipole. You have the minus, you have the plus, between the molecules, you have the interactions there. Right? So dipole. So now the next gonna be the dispersion, right? Or London, or Van der Waals, or whatever you call it, same thing. Right? So now, in which case you're gonna have the dispersion interactions between the molecule. Carbon and nitrogen? Hydrogen, yes. So if you have not only carbon and hydrogen, so I can write carbon, hydrogen, let me write CnH, 2n plus 2, right? So any alkane. If you have the hydrocarbon, what's going to be the bond there? All pure covalent. You don't have any charge separation there, right? So you don't have dipole there, you don't have hydrogen bonding there, you don't have ionic bonding. So all three we discussed over here doesn't apply when you have the pure hydrocarbon like this, just the carbon hydrogen. If you have that, the only interaction you have going to be the fourth one, dispersion, right? Or if you have like say H2 molecules, right? Just the hydrogen molecule, H2. If you have that, or noble gas, any element you have on the last column of the periodic table, all gonna have dispersion interaction. You don't have any charge separation there. So only the partial minus plus is gonna be very instantaneous. It's not permanent like dipole, hydrogen bonding, ionic. So for some conditions in the reaction, depending on that, one part of the molecule is going to be slightly induced positive compared to the other one. So they have the weak interaction, right? So this is called the dispersion. So for all alkanes you have in this chapter, just the hydrocarbon gonna have dispersion interaction. Okay? So now you're gonna compare which gonna have more dispersion, which gonna have the less dispersion. That's the question over here. Okay? So let's say these two molecules. So in this sample, you have the carbon and then 4 hydrogen, right? So this is one alkane. In the other one, right side, how many carbons you have? So 1, 2, 3, 4, 5, 6 carbon, right? So you have C6, that's 14. That's the molecular formula for that. Okay? So both, oh, I said duodecan, no, it's not 6. So you have, oh, you have 2 over here too, okay. So 1 carbon over here, 2 carbon there, 3 carbon over here, 4, 5, 6, 7, 8, 9, 10, 11, 12. Dodecane. That's the name for that. We're going to go to the naming later. But anyway, you have different number of carbons. That's the point over here. Right? So for the first one, you have fewer carbon. For the second one, you have more carbon atoms there. Or you can say, the first one is the shorter chain, the second one is longer chain. That's the point over here. Okay? So as long as you have the linear chain, N-alkane, right? So we are dealing with N-alkane over here. Right? So which one gonna have more dispersion force? Right one or the left one? Right one. Right? Do you know why? You're gonna have the more contact surface if you have the longer chain. Okay? That's the reason why you're gonna have the stronger inner molecular force. So this is gonna be dispersion, right? So not other, intermolecular. Dispersion is the only force you have there. So you're gonna have the larger dispersive force when you have the longer chain. That means you have the large area contact between the molecules, right? So that's how you're gonna find out. If you have larger area, you're gonna have the higher boiling point, higher melting point, right? All physical properties. So of course, the longer chain is gonna have the higher boiling temperature. You can compare over here. So for methane, you have negative 164. But for the other one, you have the positive 200. Very high compared to the first one. Right? That's why the boiling temperature of octane is going to be higher than propane, the cooking gas. Because they have the different number of carbon. Octane is longer than propane. Okay? So now, the next thing gonna be, what about the branched one? So if you have any branch there, then what's gonna be the value? More or less? If you compare the straight chain or the branched chain, if you have the same number of carbon, say for example, I'm gonna have 1, 2, 3, 4. That's N-butane, right? Or N-alkane, you can call that. I have 1, 2, 3, and then I have the CS3 over here. So let's say just carbon, right? You have the same 4 carbons on both sides. The first one is N, linear. Second one is branched. Okay? So now, which one gonna have more dispersive intermolecular force? Second one, right? Of course, now the second one. First one gonna have the smaller than the right one. Correct me if I'm wrong. First one, right? So this gonna have the higher dispersion or dispersive force, if you call that. What is the reason? You have the more contact area for the first one compared to for the second one. You're gonna have contact up to 3 carbons for the second one. For the first one, you have contact up to the 4th carbon. Okay? So that's the reason why always, if you have the same number of carbon, if one is linear, other is branched, then you're going to choose the linear that has the greater intermolecular force. Okay? That's the point. Let's do some practice over here. So now you know linear, branch, ionic, dipole, dispersive, all forces. So the strength is going to be ionic, going to be strongest one. Less than that going to be hydrogen bonding. Less than that going to be dipole. Less than that going to be dispersion, that is longer linear. Less than that going to be either the shorter chain or the branch chain. Okay, so that's the rank you're going to have. The strength of intermolecular force. So now you're going to rank these given molecules in such a way that you're going to have the least water soluble to most water soluble. Okay? So ionic going to be, of course, the most soluble, right? The same trend. Little bit less soluble than that going to be hydrogen bonding. Little bit less than that going to be dipole. Less than that going to be dispersion, right? So less dispersion going to be more soluble. More dispersion going to be less soluble, because the dispersion going to involve the non-polar molecule. If you recall, like dissolves like, water is polar. So more non-polar going to be least soluble. Okay. So now A, B, C, D, E. Which one going to be the most soluble? You're going to choose something that is ionic. That's the most soluble, like table salt, for example. Right? That's the one you can dissolve most of the amount there. Quickly soluble or more soluble, right? So which is ionic over here? So lithium chloride, right? So that's going to be number one, the most soluble. So what's going to be less than that? You're going to have, do you have dipole over here? Yes, you have dipole, right? So this is dipole, and then this is dipole with special hydrogen bonding there. You have OH, right? So the hydrogen bonding is going to be stronger than just the normal dipole. So you're going to have number 2 for that. And then of course number 3 is going to be close to that, which is dipole, right? Now what after that? So now you have the dispersion. So both are non-polar. So you have the dispersion force there. Okay. So now which has the more non-polar character? Longer the chain, is going to be more non-polar, right? So the more non-polar going to be less soluble, because like does not dissolve on like. Like dissolves like. Okay? So that's going to be the least one, right? So it has to be least one. So this one going to be number 4. This one going to be number 5. You're going to rank based on that. Right? 1 going to be more soluble. 5 going to be least soluble. Okay? Good? Alright. I think we're going to stop over here. Thank you.